So I'm going to start. We're going to talk about analyzing images with deep learning and Apache Spark today. So just letting you know in case you're in the wrong room. Just a little introduction about myself. I am Raela Wang. I'm a solutions architect at Databricks. I've been at the company for about 3 years now. And I specialize in machine learning solutions. So I've built a lot of scalable machine learning applications with companies all across the globe. So who here has heard of Databricks before? Okay, that makes my life a little easier. So we are the company founded by the same 6 creators of Apache Spark. And we believe that there's a lot of value in bringing Spark to the enterprise in a unified analytics platform where we can bring data scientists, data engineers, data analysts, business analysts together. Basically, anyone in the organization who requires data access will make it, make their lives really easy with the unified analytics platform. We've also trained a lot of Spark users on the Databricks platform, and till today, we still contribute about 75% of the open source code. So here's a diagram which tries to explain what we do. I'm going to start from the bottom. We are available on both Azure and AWS. We are powered by Apache Spark, so you see that that's the core of our platform. And we've built our own performance optimizations and performance improvements on top of Spark. So that's what we call the Databricks runtime. And if you have existing Spark workloads running outside on an open source Spark cluster, you might find that just taking that workload and running on a Databricks cluster, it will run many times faster. So you can use our open source Spark connectors to connect to any data source. So it can be like Hadoop, data sources, relational databases, streaming data sources like Kafka, or flat files like Parquet, for example. Use Spark for your ETL pipelines. We have this feature called Databricks Delta, which is what I would call an optimized Spark table. It is based upon Parquet files. And we've done a lot of ways of managing those Parquet files, so like optimizing file sizes for performance querying, and also different things built into it to make your queries run faster. So that's Databricks Delta. And once you're done with all the ETL with Spark, we move on to the machine learning and advanced analytics side of the house. So we are able to use any open source machine learning framework on the Databricks platform. So you're not limited to only Spark MLlib. You're also able to use packages like Tensor Flow, tree-based algorithms from XGBoost, or for deep learning, there's also Horovod. All of these packages are available out of box from the Databricks runtime as well. So on top of the runtime, we have a collaborative Databricks workspace, which has a notebook interface for you to run your code on. And we have automated jobs, so you're able to convert your notebooks to a schedule-based job. And we have REST APIs for you to fire those jobs really easily and integrate with other services that you might have. On the right-hand side, we have ML Flow, which is kind of the new project that we're working on recently. And it is an open source project, just like Spark. And ML Flow is really there for you to manage the end-to-end life cycle of an ML model. So think of it like DevOps for machine learning models. So that kind of is the Databricks platform. I will be doing a demo on the platform today, which is why I thought it would be valuable to take a look at what we are as a company and as a platform. So this talk will be covering a deep learning pipeline built on top of Spark. And we're going to take a look at satellite images and see how we can do an object detection pipeline with deep learning and Apache Spark. So I will be doing the demo on Databricks, so we'll see that in a second. So there are a lot of new use cases with satellite imagery. If you have satellite images, you can detect floods, areas that are affected by floods, fallen trees, road damages, or even figuring out if roofs are suitable for solar panels without even having to do like an on-site visit. You can just survey neighborhoods from satellite images. And also, interestingly, it can also prevent insurance fraud. So things like, maybe not so common in this part of the world, but in more tropical areas, people might be building like private pools in the backyard without declaring them, which is potentially insurance fraud. So as technology is advancing, it has become really, really easy to collect more data, and also the quality of the data is getting better. So in this case, what I'm referring to is actually, the quality of our images are getting better, higher and higher in resolution, and it quickly becomes a big data problem. So traditional tools for handling this geospatial workload is not designed for scalability. So you might be familiar with maybe PostGIS, GeoMesa. Those are tools that are great for geospatial analytics, but aren't designed to scale to multiple machines. And then comes the problem of pipelining. So you might be using different packages in different parts of the pipeline. How do you bring all of them together at scale? So we're going to look at an example of how we can identify vehicles in satellite images. And it kind of looks like this. So we have JPEG images that kind of looks like that. And we're going to try and pick out the buses, cars, and trucks. And we'll try to do some data science out of that. So how does Spark help in this sense? Well, we see Spark as the glue of big data technologies that exist in isolation. So you might be using something like OpenCV or PIL for your image manipulation. There are a lot of other deep learning frameworks out there for your deep learning use cases. So in my example, I'm using Tensor Flow, but you might be using something like Keras or other packages out there like PyTorch. For geospatial analytics, again, PostGIS, GeoMesa, also Magellan, which is based on top of Spark. And visualization, I'm only listing the two that I use in my demo, but I'm sure you guys are familiar with all the different packages out there for visualization. So, you're using different packages in, all throughout your pipeline. How do you tie all of these libraries together at scale without having to care about how you're going to store the intermediate data, passing data from one package to another, or, figuring out how to deal with the intermediate data representation? So we have a visual representation of the pipeline here. We start off with map data, and that's lots of JPEG images that I have in S3. I've worked on the demo on AWS, but the same demo should work exactly the same way with blob stores on Azure. So I have map data in JPEG formats, and I'm going to have some XML metadata on that as well. So XML metadata consists of a lot of information, but what I'm interested in is the coordinates of each map piece, and I'll need those coordinates for visualization later. So I'm going to join the map data images with my metadata, put it through some transformations with Spark UDFs, and this is where I can use packages like OpenCV and PIL and distribute it across my cluster. Once I'm done with the transformations, I'm going to put the process data into my deep learning model, generate some predictions, classify the objects identified to be a car, bus, or truck, and then I'm going to do a deeper dive into the prediction results with Magellan. So for those of you who are not familiar with Magellan, Magellan is a geospatial analytics package built on top of Spark, so it's powered by Spark SQL. And then we're going to take a look at visualizations and take a deeper look at our results. So let's jump straight into the demo. Can everyone see? Good? Awesome. So what we're looking at here is the Databricks Platform. And we're going to start off with the cluster manager here. And you can see that I have a lot of up and running clusters here and other terminated clusters over here. So it's really easy to connect the Databricks Platform to your AWS or Azure accounts. And you can easily use the platform to spin up resources that you need and run your Spark workloads on them. So I'm not going to run through this in great detail, but I just wanted to point out the Databricks runtime versions. So we package Apache Spark along with performance improvements to make it run faster, which is what we call the Databricks runtime. And we can spin up CPUs, GPUs, and we also have this other runtime called the ML runtime. And it's also available on GPUs. So the ML runtime will pre-package a lot of your machine learning frameworks in them. So things like Tensor Flow, Keras, PyTorch, they are all pre-packaged in your cluster image. And also, if you spin up a GPU instance, we deal with all the library dependencies for you. So you can just click this, launch the cluster, and start with your analytics straight away. We also have auto-scaling built into the product. We scale according to Spark tasks. So again, we are a Spark company, so we've built a lot of features here to be very tuned to Spark. And we also have auto-termination here so that if you're not using the cluster, we will shut that down. So things like auto-scaling and auto-termination are built in really for you to lower your total TCO. And once I have a cluster, I'm going to use this particular one. So that's the cluster I'm going to use, and the instance type I'm using on AWS. And what's cool is you can actually we can actually share this cluster with different people in the team. So, for the DevOps guys in the room or, the managers in here in this room, you might be a little concerned of having so much people on this platform and they're just going to go trigger happy and spin up 100-node clusters and it's going to go out of budget really quickly. What we can do is we can restrict cluster creation permissions and create these cluster templates beforehand with specific configurations, and then assign different people or different teams access to attach, restart, or manage those clusters. So that's the cluster permission piece. And once I have a cluster up and running, I'm going to jump straight into the demo. So I already have all my libraries attached to this particular cluster, but let's just take a little look at what I have on this particular cluster. So I have Magellan, which is the geospatial analytics package based on Spark. I also have Spark deep learning pipelines, which is what I'm going to use for the deep learning portion of the pipeline. Spark XML, which is what I'm going to use to parse my metadata, as well as Tensor Flow. So these are all libraries that I've created with our library UI over here. And you're free to attach any package that you have onto the Databricks workspace and onto your cluster and have that readily available to all of the users on the platform. So in this notebook, what we're going to look at is, the pre-processing and ETL portion of our pipeline. So we're going to load the satellite images from S3, do the joins with XML data, and then, do some UDFs to do the pre-processing. So let's take a closer look at what that looks like. So here in S3, I have my JPEG images. And this S3 bucket is mounted to DBFS, which is our Databricks file system. It's really an abstraction layer on top of S3. So this data remains in your S3 buckets or Azure Blob Stores and in your responsibility and in your account. And then I also have a different folder for my XML metadata. So I'm just going to pull up my XML file here. It's a typical XML file. And I'm really only interested in this portion of the XML file, and I'm not interested in the rest. And what I'm going to do is I'm going to use the Spark XML package to load in that data, specify a specific tag that I'm interested in, and it will pull, and Spark will handle the rest and present it in a nice, pretty table format. And if I scroll here, we should see the coordinates in this column. So this is what I'm interested in. The coordinates are in British eastings and northings format, which is really, really new to me. So I have to figure out how I'm going to convert them into latitudes and longitudes. So that's part of the ETL process as well. So now that I have my XML metadata, I have a Python script in another notebook, which I have as, I'm loading it in as a helper function. So you can see that I'm running a %run. And this is actually a different notebook in the same folder that I have here in my workspace. So let's just take a look at what that script looks like. I just copied it off of GitHub, so I didn't write this code. But basically, it's a Python, really long Python function that does the transformations from British eastings and northings to latitudes and longitudes. And it's a really long Python script. Really long. Don't ask me why the UK uses that system. But what we're going to do here is I'm going to just put this whole Python script into a Python function and register it as a Spark UDF. And what I can do here is, with my coordinates here, I'm just going to pull that up into a flat format, so unnest my data here, and apply this UDF to my Spark data frame. And here you can see that it has been, exploded into a flat format and converted into latitudes and longitudes, which is great. So now we're going to load the images, and I'm using Spark 2.3 here to load the images. This is a new API in Spark 2.3, so it's not available in Spark 2.2. And this read images API is able to read in JPEG images, for example, into a format that will play nice with Spark. So you can see here the schema of the data. And I'll have the associated file paths as well. So here you can have a little look at what my data looks like. I'm just going to zoom in because it's a little tiny. But you can see that I have a lot of information in each square. So the data that I have comes in 1 kilometer by 1 kilometer squares. And there's a lot of information in each 1 km by 1 km square. So in order for our deep learning pipeline, deep learning model to play nice with my data, I have to cut each image into smaller pieces because it's impossible for my model to detect like millions of objects with the current infrastructure that I'm using. So what I'm going to do is I'm going to cut each 1 km by 1 km square into 100 chips. And I have another UDF that does that. So again, I wrote zoom out. Again, I have a Python function that does that. So the goal here is to really make the images smaller so that I can pass it into my deep learning model. And then when I have a lot of small images, it's going to be easier to distribute it across multiple machines instead of having fewer huge machines. So as I'm cutting the images, I have to retain and generate the respective latitudes and longitudes in order to plot them on a heat map or a world map, for example. So again, this is a really long Python function, and I'm going to put it into a Spark UDF, and I can run that on my Spark data frame. So here, let's take a look at what the chips looks like. And I have the respective latitudes and longitudes for the southwest corner and the northeast corner. So that's the bottom left and top right. You can see that there are less, objects within each image, which makes it more manageable. And once I have this, I'm going to persist everything out into Parquet, back into S3. That includes the images, the latitudes, the longitudes. I'm just going to persist everything into Parquet and into S3. So now comes the fun part. We have finished the processing and the ETL portion of our pipeline, and we're going to move into the deep learning side of the story. And what we're going to do here is we're going to use the deep learning pipelines package to load a Tensor Flow model. So this Tensor Flow model has already been trained, and it was actually not trained by me. If you're familiar with the XView dataset, which was released as part of the XView data challenge. You might be familiar with the Netflix challenge, which was for recommender systems, and they had a really great cash prize. So they have a similar challenge for XView, which basically is an object detection pipeline on satellite images. So that model was trained on these satellite images. So it's kind of different from what we saw in my example. What I'm going to do is they released a baseline model in TensorFlow, and I'm going to use that model and apply it on my satellite images. So here, I have that model in a PB TensorFlow format in S3. I'm going to load that in and put it through my TF image transformer, which is a helper function within the deep learning pipelines library. So what I can do here is I've loaded the TensorFlow model, and I can do predictions on a huge Spark data frame and generate a lot of predictions in parallel. So here you can see the input column to the transformer is my image chips. And I'm going to generate, detection boxes, scores, and their respective classes for how they have been classified. So example of classes would be like bus, car, or truck. So I'm going to call a transform on my Spark data frame. And now I can take a look at the predictions. So what happens is there's going to be a lot of objects within each image, and we're going to get it in a nested format. So it's going to be like a nested JSON for each image with a JSON of all the objects that I've detected. So I have to call it explode to flatten that out. And this is what it looks like. So what I did is I actually looked for cars in this example. And if I've sorted the results by prediction scores. So you can see that this one is about 0.89, which is pretty high. And you can see kind of looks like a car, which is great. Looks like our model is working. So what we're going to do is we're going to try and visualize this on a map. And again, I have another function to do the plotting for me. I've run that in as a helper function. It's a Python function that we're using here. And we'll try to plot all the cars on a map. And that looks like this. So our data set consists of maps from London. And you can see that here we have a higher concentration for cars. And that's great. Looks like the model is working. Let's zoom out a little bit. And you'll realize that the center of London has hardly any cars, so it looks like congestion tax is working. And it's a good thing that the model is working too. And if you look at, I guess this area of London, that looks like there's a lot of cars here. And I think this corresponds to some major highway in London. And if I zoom in here and take a look at Hyde Park, which is a really nice and beautiful park in London. If I maybe zoom in a little bit more, you can find cars in the water and cars in the trees. So it kind of shows the limitation of using a model that was trained on another data set. If I train the own model with my own data, perhaps I'll get better predictions. So obviously, our model is not doing very well here. It's picking up some weird stuff in the water and saying it's a car, which is not super awesome. But in general, for most of the Hyde Park, it's quite a good result to not find lots of cars in Hyde Park in general. It's a good sign. So what we're going to do now is we're going to take a deeper dive into the predictions here. So here I'm going to use Magellan to run some queries on the data in Hyde Park and see what's going on there. So here I'm just going to import the Magellan classes. And here I pass in the coordinates, latitudes and longitudes of Hyde Park and generate a polygon. And with Magellan, I'm creating a Magellan polygon here. And what I'm going to do in Magellan is I'm going to pass in my Spark data frame and look for cars. Cars has been hard-coded to class 18, so that's how I know it's a car in my example. And what I'm going to do in Magellan is I'm going to use this API here to say pull out the data that is within this polygon, which is Hyde Park. So again, I'm going to do a sort by score and put the best results on top and the worst results at the bottom. So the first few have pretty high scores, and you can kind of see, let me zoom in a little bit more, kind of see that they look like cars, which is great. So I guess there's a parking lot in Hyde Park, and there are some cars there. I'm not super sure, but that kind of makes sense to me. And if I scroll down a little bit more to look at the objects that have very low scores, this kind of looks like a bench in the park. And if I scroll down, this kind of looks like two tables. Maybe it's a car, I'm not super sure. Again, having higher resolution images will help here. And this kind of looks like three cyclists. So it's interesting to see that, we've detected cars, and that maybe gives a pretty good result. And if we take a deep dive into a particular geolocation and zoom in and take a look at the results, we're classifying some other objects as cars, so things like cyclists, tables, or benches in Hyde Park as cars. And that's all I have in this demo. And as a recap, let's just take a look at what we did here. That's not the slide. We've read in the images from Spark. We have XML metadata as well, and we did a join for image data with XML data. We parsed that data with OpenCV with Spark UDFs, and we are able to also do a UDF to do a coordinate transformation. And we also did a pre-processing step that cuts my images into smaller pieces so that it's easier to parallelize and also cheaper to use smaller machines. And I used a pre-trained Tensor Flow model, loaded it into Spark deep learning pipelines, and generated huge predictions across my Spark data frame. And I was able to visualize my results on a heat map. And I did a cross-check of the results with Magellan to kind of zoom in into a certain geolocation and take a look at why my model made certain results or predictions. Thank you, everyone.